Well, here we go. The next lecture, 10.5. I just thought I'd point out that I'm recording this at noon on Sunday, but you need not worry. The Packers don't play for a couple hours. They play at 3:30 this afternoon, so you don't have to feel bad for me, although I'm sure you probably don't. So here we go. Let's go full screen here. Full screen. Now, today, we're going to do some more tests, specifically as you saw on the front page there. We're going to look at, in black, I always start off in the wrong color, the ratio and root tests. Now, at this point, you may be getting sick of all these tests, and some of you, the skeptical ones, right, and good mathematicians are skeptical, are wondering, why are we doing this? Why? Why are we doing this? And the answer is we're in pursuit of what's called a Taylor polynomial. And we essentially are trying to model any function with a polynomial, and we have to prove that this polynomial, if we add enough terms, x to the fifth, x to the sixth, etc., will converge on the function that we really want to model. So bear with me. We've got a couple more days of tests, and then we can really start to work with some powerful mathematical tools that apply to mathematics, physical sciences, engineering, all that stuff. All right, so let's set the stage here a little bit. Recall this thing called the geometric series, right? And it seems like so long ago. Wasn't it simple when things were just geometric? And how did that work again? We knew that the sum from n equals 1 to infinity of some kind of first term, and we call that a, times the common ratio n, equals, well, I'm going to go back and erase this here, because really the way I've written this, it needs to start at 0. And think about, why does this need to start at 0? Equals a plus ar plus ar squared plus ar cubed plus dot dot dot. Right, so you can see, in order for this r to go away here, I needed to say that it starts at 0. Alternatively, I could have written this as n minus 1. But just understand this notation. That's still important to know. And we say that r is defined in this triple equal sign. Remember, that means defined as the common ratio between a sub n and a sub n plus 1. So if we say that r equals this ratio, a sub n plus 1 divided by a sub n, well, that equals a times r, right, to the n plus 1, over a times r to the n. And I know that that equals, I can break this n plus 1 into an a times an r to the n over a times just r to the n. And then if I cancel some of this stuff out, well, I can see that the a's cancel and the r's to the n cancel. So what am I left with? Just r. I just said r equals r, which seems like I just went in a big circle, right? I defined r, I defined the series, and then I said that r equals r. Well, remember that this converges when r, the absolute value of r, is less than 1. Well, that leads us right in, as you might guess, to the ratio test. The ratio test is here in 10.5, ratio test JPEG. Get this one down here. Now what does this thing say? Let sigma a sub n be a series of positive terms, blah, blah, blah. Suppose that the limit as n approaches infinity of a sub n plus 1 over a sub n. So the ratio, the limit as n approaches infinity of the ratio between these two terms. The next one over the first one, right? So here's this one, here's the next one. Just like I did up here, where I did this ratio. Except that here equals this letter rho. And that's the Greek letter rho, which is the equivalent of our Roman letter P. R. But don't get these confused like I just did. And just for the sake of notation, my rhos usually look something like this. And that's pronounced rho. And my P's, I try to look them like, you know, they have a square tail and this little, I don't know what you call that thing. It's not really a serif, but something. That's the letter P, which I guess we have to spell like this. But this is like the Greek letter R. All right. And this letter, and so don't call this P, because it's not P, it's not a power, it doesn't stand for anything that starts with P. You'll see rho show up a lot of times, radius, ratio, you know, things like that, root. The Greek letter rho often shows up. So sorry about that page, middle row. Greek letter for you. Now, I'm not going to go through and prove this thing down here, because I think the proof, it's kind of formal, epsilons and deltas and that sort of thing. If you're into that, you should read it in the book. But very similar to this up here, I'm back on the left page here. If the series converges if rho is less than 1, right? So if there's some ratio between a term and the next one, and at the very end, the rho is less than 1, the series diverges. If rho is greater than 1, and rho is infinite, so if it keeps getting bigger. The test is inconclusive if rho equals 1. So I'm going to go off my notes here a little bit. And what if we said the limit, if we looked at the harmonic series, and that is the sum n equals 1 to infinity of 1 over n. So if we applied this ratio test, we're looking at 1 over n plus 1 over 1 over n, and this is our rho. And you can quickly see that this just becomes n over n plus 1. And we could factor out an n or do a number of things, but we can see that the limit as n approaches infinity of n over n plus 1 equals 1. So this, we certainly can't use the ratio test to show that this converges. So this would be an inconclusive case. Inconclusive. All right, let's take a look at another example here. And this one, this one takes a lot of room, so I'm going to skip to the next page. So we'll look at another example up here. How about this series n equals 1 to infinity of 2 to the n over n factorial. Right? Does this thing converge? Well, if we want to do let's take a step back and say, does this, what would we normally do? We'd say, well, 2 to the n, that certainly grows big, right? So this could be infinity over infinity. So one might think, well, I can apply L'Hopital. But we don't have a good derivative for the factorial, so that's not going to work, and we know both these are going to grow. Tough call. So let's write out a few terms. So the first term would be 2 over 1, plus the next one would be 4 over 2, plus the next one would be 8 over 6, plus the next one 16 over 24, and the next one is 32 over 120. So I'm looking from one to the next here, and like I don't see any obvious common ratio. Let's simplify these. 2 plus 2 again, plus 4/3 plus 2/3. Now at least we're under 1, plus 8/15 plus dot dot dot. Well, that certainly didn't clear anything up at all. So here's where we say maybe at some point way down the series in what we call the tail of the series, maybe there is some sort of common ratio. So we'll take a look. We'll say that rho equals the limit as n approaches infinity of 2 to the n plus 1 over n plus 1 factorial. So that's the next term divided by the current, 2n over n factorial. Now we have to do a little algebra as usual. This becomes 2 to the n plus 1 over n plus 1 factorial, and we multiply that by this guy here over 2 to the n. Now, n plus 1 factorial, n factorial, 2 to the n plus 1. There's a lot of plus 1, so we really have to be a little bit clever and just kind of have faith and power through this thing. 2 to the n plus 1, well, that's 2 times 2 to the n. And n plus 1 factorial is n plus 1 times n factorial times n factorial over 2 to the n. And now things start to cancel out for us. Let's see what we can clean up here. 2 to the n, that definitely goes away here. The n factorial goes away there. Well, that's nice. Now all our exponents and factorials are gone. So that leaves us with just down here 2 over n plus 1, which equals 0. Now I'm not just saying a sub n goes to 0. I'm saying that the ratio between these two things goes to 0. And that's enough to go back to our theorem. Let's say it's less than 1. Rho is less than 1. It's 0. It's kind of a special number less than 1, but it's still less than 1. So we know this thing converges. Good. Now let's take another look, another example. That doesn't make any sense, but whatever. You know what I'm trying to say. 2 to the n equals 1 to infinity of 2 to the n. No, is this what I meant? Oh yeah. This one looks a lot alike, but it's not. And to the 20th. Does this converge? Well, as you might guess, we're going to cut straight to the ratio test. So rho equals the limit as n approaches infinity of the next term, which is 2 to the n plus 1 over n plus 1 to the 20th. Well, that's going to be kind of strange. Over 2 to the n over n to the 20th. Now the algebra here, how does this look? Well, for starters, we can invert and multiply as usual. 2 to the n plus 1 over n plus 1 to the 20th times the reciprocal here, n to the 20th over 2 to the n. And what do we do? Well, this thing we can break down like we did before. That becomes 2 times 2 to the n over n plus 1 to the 20th. Well, let's leave that for now, because I don't know exactly what that's going to look like. Times, what do we have left? N to the 20th over, where am I here? 2 to the n. So let's go through and cancel. I don't think there's as much to cancel out here, but 2 to the n definitely goes away. So we're left with this stuff, okay? N to the 20th over n plus, here we have n to the 20th, n plus 1 to the 20th. Oh, and they both have the same exponent, so I can say that's n over n plus 1. That whole thing goes to the 20th. And then I've got just a 2. Is that all I have left here? Yeah, just a 2. Now n over n plus 1, right, that just becomes 1. And so 1 to the 20th is 20, so this whole thing equals 2. Now what does that mean? We go back to our theorem here. Let's see if diverges if rho is greater than 1. Rho is greater than 1 for sure. So 2 is greater than 1. Therefore, this diverges. Okay. Let's look at one more example on this one here. These examples are all a little less than a page, so I feel like I'm wasting a lot of paper. How about does the sum n equals 1 to infinity. Let's put the factorial on top this time. Over, how about n to the n? N to the n. Now what's that thing going to do? Does this thing converge? Let's do the ratio test. Rho equals limit as n approaches infinity. N factorial becomes n plus 1 factorial over n plus 1 to the n plus 1 over n factorial over n to the n. Boy, this could be some funky algebra by the time we finish this up. Then invert and multiply as we always do. N plus 1. You never thought you'd do so much inverting and multiplying in calculus, did you? N plus 1 to the power n plus 1 times, this will be n to the n on top, over n plus 1. No, yeah, n plus 1 to the n plus, no, n factorial. Okay. The factorials boil down pretty nicely, and so I can say this is, this is all still the limit. N plus 1 factorial is really n plus 1 times n factorial. And we know on the bottom, n plus 1 to the n plus 1, well, if we just kind of forget about that the base looks funny, I could just say this is n plus 1 times n plus 1 to the n. And then the second part is n to the n over n factorial. Now we can start doing some canceling. N factorial, okay, that's going to go away. N factorial up there. We have n plus 1. We have n plus 1. So now what do we have? We're left with n over n plus 1. This is to the n up here, and this is to the n down here, so that equals n over n plus 1 all to the n. Okay, now this looks a little bit like one of these limits I did way back in chapter 10.1, I think it was, several sections ago, except it's a little bit upside down. So I'm just going to make it right side up by putting it over 1, n plus 1 over n, and all this thing is raised to the n. And I can split this up into two fractions, and so it becomes 1 over n becomes 1 plus 1 over n, this whole thing to the n. So remember, with limits, I can use the quotient rule, and I can split this up into 1 to the n over 1 plus 1 over n to the n. 1 to the n just remains 1. And 1 plus 1 over n to the n, I know that equals e to the 1. So this becomes 1 over e. E is like 2.7 something, so this is definitely less than 1. So this thing converges. Good, good. Now, we've done a few examples here. Let's take a look at the examples we did. N factorial over n to the n. So that one's got a factorial and some exponentials in there. This has got a constant to an exponent, and then so this becomes an exponential, and this is an exponent with an n, more of the same, exponents, factorials. So in general, we could say that this this ratio test works well. The ratio test works well for things that that kind of smell like or include n factorial, some common ratio to the n, or maybe an n to the n, this type of thing. But we can oftentimes apply, often we can apply a simpler test. And that simpler test is as follows. It is called the nth root test. And here's how it looks. Let the series, so all a sub n's are positive at some point. Maybe it starts out negative, but then it winds up being positive at the tail of it. And here we decide to define another row. This time it stands for root instead of ratio. And the nth root of a to the n, as it goes to infinity, same deal. The series converges if the root is less than 1. The series diverges if the root is greater than 1, or it goes to infinity. And the test is inconclusive. So the results become very much the same here. Still it's a row. So we could apply kind of a overly simplistic example, and that looks like does the sum from n equals 1 to infinity of this big thing here, 4n squared minus 3 all over 7n squared plus 6. This whole thing raised to the n power. Does this converge? Well, let's define rho as the nth root here. So that becomes the nth root of this whole thing, 4n squared minus 3 over 7n squared plus 6 to the n. Well, that one seems obvious. We're taking this raised to the nth power, so it seems obvious to take the nth root. This becomes 4n squared minus 3 over 7n squared plus 6. Now we have two options. Option A could be l'hôpital, right? And that would lead to the 3's and 6 would go away. 8n over, let's see, 14, and then take the derivative one more time, is 8 over 14, which is the same as 4 over 7. So L equals 4/7 here. Or we could do some factoring. Oftentimes, factoring works at the same time L'Hopital, and that would lead us to believe that L equals 4/7 as well. 4/7 less than 1. Okay, this converges. In the last example, I know it's almost over. You guys just are getting warmed up. We find up here. This one's a little less obvious. What about the sum? And let's throw some more exponents and stuff in here. N equals 1 to infinity of 2 to the n over n to the 10th. What does this thing happen? So if we take the nth root of this guy, so the nth root of 2 to the n over n to the 10, well, that's raising it to the 1 over n power, so the top just becomes 2, and the bottom becomes n to the 10 over n equals 2 over n to the 1 over n, and this whole thing raised to the 10th power. And I know that that equals 2 over 1, which equals 2. So this means it diverges. Now you may be wondering, why is this 1? Right, and that's a good question to ask yourself. I'm going to leave that to you guys to answer. So that's it. Pretty simple. Two fairly straightforward tests today, and you can apply those to the problems on the homework. Most of them are really pretty straightforward. A little tricky algebra is the worst of it. So I will see you in class.